We're continuing with section 4.1. I click at question 2. The question is asking, peeling an orange changes its volume V. What does delta V represent? And I recommend stopping the video and thinking about this. I hope you stopped the video and thought about this a little bit. And so let's discuss this. What is delta V? The change in volume. I know that the amount that is changing, the absolute value that is changing is the rind, right? It's the volume of the rind. But since V is decreasing, the delta V has to be a negative value. The volume of the rind is a positive value, so I have to multiply that by a negative value to get the change in volume. So D is the answer. Now let's talk about error estimation. So sometimes we're in physics lab, for example, we're measuring a value. And that value has our devices have a certain limits. And so we have an error in approximations of values. Now let's assume that, let's say, the value that we're approximating is a length, and we want to figure out a volume. So I have to use my faulty measurement in another function and find the output of that function. Output of that function, because the input was basically had some error in measurements, will have some error in measurements. It's important for us to limit the error for output. So one of the ways to figure out this error is in Calc 1 is tangent line. And of course in Calc 2 and Calc 3 you learn more. Calc 3 you learn about multiple measurements that give you an output. In Calc 2 you learn other methods of finding errors. But Calc 1, most physics lab use the Calc 1 until there are multiple measurements to plug in, which is Calc 3. And so let's see. And also we give you some examples of everyday life. Now let's assume that your input is what you're measuring in the lab has error delta x. We call that d of x. Delta x and d of x are the same thing at this point. Then what I do is, and you measure the value and it's a. So I'm plugging it into the function. Let's say function is the volume, and I'm getting f of a. But let's say your approximation could land anywhere in here, right? And so how bad does it work if the actual measurement, input measurement, would have been x over here, right? And x over here, what I would get is this value, not that value. So why I would get f of x, not f of a. So the difference between f of x and f of a is the actual error. It's delta y. But if I had any way to measure this correctly, I was not even discussing it right now, right? So I want to approximate the error that I made. And approximating the error that I made is I use the tangent line at f of a. And I say, well, if I had used the tangent line, I would have approximated this y f of x value to be this value, LA of x. And the difference between LA of x and f of a is basically, we call it dy. What is it? So I'm saying the difference between LA of x minus f of a. If you subtract what you have before, this is going to be f prime of x, f prime of a, I'm sorry, times x minus a. Let's look at this. What did we call delta x? We called x minus a delta x, right? All of these are going to have an absolute value around them, but I'm just discussing it when x is bigger than a at this point. And then we say that all of these are going to have absolute value around them. Now, therefore, and then I'm saying that this is actually this value, which is dy. So different, the y of the tangent line minus f at the point A, at the nice point, or at the measurement point, is going to give me f prime and the difference between the actual value and the measurement point. And that's how we approximate error. And so again, delta f is the same thing as delta y, and it's the actual value at the of f at the point minus the value of f at the measurement point, and df or dy is the f prime times delta x. And this is easily seen through the tangent line approximation that we discussed. Again, so one more time, repeating the same thing. Linear approximation error if the value of x is measured at x equal to a with an error of plus minus delta x. Then delta f, the error is estimating f of x, can be approximated by delta f equal to f of x minus f of a approximated by f prime of a delta x equal to delta f. So again, here plus minus delta x, and I switched it to a positive value here, or absolute value of the actual error. Now, so example 2, in standing 100 meters from a building, so this is my building, here's the building, and then you're standing 100 meters from the building, and you're looking up, and let's say you're laying down on the floor, and or your height is negligible, one of the two, and then this is 100 meters, and then the angle that you see the building is 60 degrees, right? How can I measure the height of the building? That's the first thing. How tall is the building? How accurate is your approximation if your measurement of angle is within 3 degrees error? So again, what you're measuring is the angle, theta equal to 60 degrees. That's your A equal to 60 degrees. Well, I don't like 60 degrees, do I? Because differentiation is going to cause trouble. So instead, I'm going to go to radian, which is pi over 3. And pi over 3 radian, right? And so, or I can call this, again, I wrote A, so you remember that's the point that we're measuring at. And then delta x is going to be equal to 3 degrees. Again, I don't like degrees. What do I like? I like in radian. So I go 3 times pi divided by 180. And I get pi over 60. 3 times 6, 180. So that's the delta x that I'm getting. That's the input is changing by pi over 60. Now that's the story told, right? So first of all, let's figure out how tall is the building. The building, if I use how tall is the building at the approximated value. And so that would be, this is the height. This is the height. And this height, what I see is height divided by 100 gives me tangent of theta, or tangent of x, whichever you want to do. And so using this, I can actually measure the height. And theta is pi over 3, so height is equal to 100 tangent of theta, and height is approximated by 100 tangent of pi third. Sine of pi third is square root of 3 over 2, cosine of pi third is 1/2, so tangent of pi third is square root of 3 over 2, so it's 100 square root of 3 meters. Okay, so that's a nice piece of information. What else do I need? It's asking how accurate is your estimate. And how do I find the accuracy of estimate? I have to figure out what delta y is. So let's go to the next page. And so this is my approximation, and now I have to figure out what approximate delta y. Delta y is approximated by dy. And what was y? In here, instead of y, I had h. And h was 100. Again, 100 was the value that I was pretty accurate. Tangent theta, right? So delta h is going to be approximated by dh, which is equal to derivative of this thing, which is 100. Derivative of tan theta is going to be secant squared theta, and then multiply by delta theta, and then and so I approximate that at theta equal to pi third. And so that's it. You just find the derivative, you multiply it by the change in the input. Change in output is approximated by the derivative at the measurement times change in the input. This one is derivative at the measurement times change or error in the input. And so delta h is going to be, delta h is 100 secant squared of pi third times pi over 60. And secant squared is 1 over cosine squared. Cosine squared of pi third is 1/2. So secant squared of pi third is going to be 4, and then you multiply them all together to get this value. You get 20.94 meters, and that's and look at this. This is the output approximation that you get with the measurements that you have, and this is going to be the approximation of the error that you may get, which is pretty high. So we discussed this, and sort of you know the input, the measurement of input, you know the error in the measurement of the input, you found the measurement in the output. A lot of times in real life, people are going to ask you to actually limit your output error. So how do we go about doing this? Example 3. A gaming company produces cubical dice. For shipping purposes, each die must have volume 80 cubic centimeter with a tolerance of plus minus 2 cubic centimeter. How long should each dice be, and how much variation can be allowed? Here's the question. What is the measurement, the input measurement? That would be the length. So here's the cube. And each side is, let's say, x. So the volume is going to be x to the third. And if I plug in for whatever value of x, I'm going to get 80 centimeter cubed. And I know that my x measurement has error of plus delta. The v of x is x to power 3 or x cube, and it's asking you that we want output to be 80 cubic centimeter. So and the tolerance of the output is plus minus 2 cubic centimeter. That means that delta V is going to be less than, we want delta V to be less than 2 cubic centimeter. Again, delta V is supposed to be approximated by dV, and dV is going to be basically V prime at point A times delta X. And so what I want is to figure out what delta X, what error in measurement in the input will give me the right value. Now, one thing is that I don't know what A is, so I have to figure out what A is. A over here, and then I have to figure out what delta X is. Finding A is not too bad because I know that the output V at A is going to be 80. So I plug in A to power 3 and I get 80. So A has to be third root of 80. That was not too bad, and I know dV is V prime at A times delta X. Now, I have to figure out V prime. V prime at X is equal to 3x squared, and then I'll plug in A, and so V prime at third root of 80 is going to give me 3 this to power 2, which is going to be 80 to power 2/3, right? And then what I want is 3 times 80 to power 2/3 times delta X to be less than equal to 2. And then I compute delta X, which delta X is less than equal to 2 over 380 to power 2/3, which is then, so it gives us the maximum error that we can get as we compute this. And here's the value that we get. It's going to be approximately 0.0359. So the error in measurement of the length should be pretty small, and the design length should be between, again, this was the value that we found from the the output measurement, and this is the value that we found using the tangent line in the error. And so the side length should be that plus minus this value.